Right. So in last class we discussed what is a row space and what is a column space, right? And then null space. These are the three things we discussed. So row space is nothing but the space generated by the rows of the matrix, whereas the column space is the space generated by columns of that matrix. And when it comes to the null space of a matrix is nothing but the solution space of Ax equal to 0. And that is what we call null space of A. And we see how to find basis for the row space of A. So given a matrix, let's say you're given with a matrix, first you do one thing, convert this matrix to echelon form. So convert it to echelon form, let me write it as EA, that is echelon form of A. You can convert it to reduced echelon form or an echelon form, anything is fine. So once if you convert it, then you see the number of non-zero rows and you pick up the non-zero rows, and those are what the basis of row space of A. So we have seen how to find basis with the help of the echelon form, right? And similarly you can find the basis of the column space with the help of this echelon form only. So what will you do? After writing the echelon form, you try to find out where are the pivot elements. So once if you find out the pivot elements, then you take the corresponding columns. So that corresponding columns will give you the basis of the column space. And when it comes to the null space, so first you take the reduced echelon form. We know that the solution set of Ax is same as the solution set of Ea times x equal to 0. With the help of this echelon form, like you just solve for the solution space here, it is easy to get it. And once if you get the solution space, that is what we call it as a null space. And we'll come to know how to write the basis of the null space of A. Okay. And given a matrix, we can find what is the rank of a matrix. So rank of a matrix with the help of this reduced echelon form. So after getting the echelon form, you just count the number of non-zero rows in that echelon form. So that will tell you the rank of that matrix, which is nothing but the dimension of the row space. And of course today we are going to see that the dimension of the row space is same as the dimension of the column space. We are going to see that result. Okay, so before going further, I'd like to recall this topic, that is linear transformations. So we'll discuss a little bit about it, and later we'll discuss everything related to the matrices. Okay. So we know what is a linear transformation. So when you have two vector spaces, let us say V and W are vector spaces, we are going to have a mapping between them. Let's say that T is a mapping which takes the vectors in V to the vectors in W in such a way that it satisfies two conditions. The conditions are T of V1 plus V2 is same as T of V1 plus T of V2, and T of lambda times V, that is same as lambda times T of V. Okay, so where you can see that the field of the first vector space will be same as the field of the second vector space. So you're taking a linear transformation which maps a vectors in V to a vectors in W, and which satisfies these two conditions. Then I can say that T is a linear transformation. A mapping which satisfies these two conditions is called a linear transformation. So we can look at some examples. When you take a linear transformation from R2 to R3, let's say that is T of x comma y equal to x plus y. Let me take R2 to R3 and x minus y and here x. So this is the mapping. So I am associating every element in R2 with an element in R3, right? So you can see that this is clearly linear transformation, and which satisfies the above two properties. And there is an important thing about linear transformations here. If T is a linear transformation, then definitely the image of 0 must be a 0. That is, if T is a linear transformation, then you can conclude that the image of 0 vector must be a 0. Suppose if the 0 element is mapped to a non-zero element, then you can say that it cannot be a linear transformation. If it is a linear transformation, it has to satisfy this condition. Okay, so this is one condition to just to check directly. So here 0 is mapped to 0. But remember one thing, if 0 is mapped to 0, you cannot conclude that it is a linear transformation. It is only one way, not the other way. So one way is true, the other way need not be true. For example, if I take a transformation which takes a vectors in R2 to an element in R, then I'm going to define the mapping this way: t of x comma y, which is equal to x plus y whole square. So this is the mapping I'm taking. But here you can see that 0 is mapped to 0, but you can check this is not a linear transformation. Why? Because the image of 1 comma 1, I can see this is 2 square, which is 4, and whereas the image of 1 comma 0, and that's what 1 square, I'm going to get 5, no. So let me do one thing, let me take the image of 1 comma 2, then this is going to be 1 plus 2, 3 square, which is 9. But when you take image of their sum, so the image of sum, that is 1 plus 1, 2, comma 1 plus 2, 3. So this is what 2 plus 3, that is 5 square, which is 25. Okay, so you can see that t of v1 plus v2 is 25, whereas t of v1 is 4 and t of v2 is 9. When you add it, I'm not getting 25. So you can see that this condition is not satisfied. Okay, and of course you can observe one thing: when you have a linear function, there you cannot have the square, cube, or power 1 by 2. These are all, they cannot be linear functions. Okay, so in a linear, if you say a function is a linear transformation, you should make sure that the powers must be 1 and there are no constant terms. Why? Because if there is a constant term, it means 0 will be mapped to a non-zero element. For example, if I take another transformation like t of x comma y equal to x plus y plus 1. So that is x plus y plus 1. So if you look at the image of 0, that is mapped to 1. It is not equal to 0. Therefore, this cannot be a linear transformation. Of course, the first one is also not a linear transformation. So in a linear transformation, you can make sure that there should not be any constant terms alone, and the powers must be 1. The power of x and y must be 1, and there should not be multiples of x and y. You should have a linear expressions, that's it. Okay, so this cannot be a linear transformation. So even though 0 is mapped to 0 here, but it's not linear function. Let's assume that you have a linear transformation which is defined from R3 to R2. This is defined by t of x, y, z equal to x plus y minus z, comma, or let me do one thing, let me use a, b, c. That is ax plus by plus cz, comma, dx plus ey plus fj. So this is how a linear transformation is defined. Now let us see what is the relation between a linear transformation and matrices. So for every linear transformation, we can get a matrix here. So this is how you can get the same mapping can be written as this xyz. I'm going to write it as xyz, and this is what we call coordinate vector of xyz with respect to the standard basis. And this one I can write it as a, b, c, d, e, f multiplied with x, y, z. So the same transformation, you can express it in terms of a matrix multiplication. So that is t acting on x is same as a multiplied with x. So every linear transformation can be expressed this way, right? So this is the matrix representation with respect to the standard basis. For example, what are the standard basis of R3? I am taking the standard basis of R3. They are nothing but 1 0 0 0 1 0 0 0 1. Yeah, and similarly the standard basis of R2. So the standard basis of R2 are nothing but 1 0 0 1. Now first I am going to see what is the image of 1 0 0, the first element in the basis set. So the image of 1 0 0 is, you can see that is a comma d, right? Now this you have to write it as a combination of basis elements here. So the basis elements are 1 comma 0 and 0 comma 1. So this a comma d can be written as a plus a into 1 0 plus d into 0 1. So therefore the first column of the matrix is the coordinate vector of T of 1, 0, 0, where the coordinate vector is nothing but when you express an element in terms of as a linear combination of basis elements, then you take the corresponding coefficients. The corresponding coefficients are A, D. So this is the first column of the matrix. So I can see the first column of the matrix, it can be obtained by taking image of the first basis element. Similarly, the second column you can obtain when you take the image of the second basis element. So the second basis element here is 1, 0, 1, 0. So its image, the image of 1, 0, 0, 0, 1, 0. So 0, 1, 0, this is nothing but D comma E. So this can be written as D into 1, 0 plus E into 0, 1. And similarly, you can see what is the third column. Third column is image of the third element in the basis set here. That is the image of 0, 0, 1. And that you need to express it as a combination of the basis elements here. So since it is a standard basis, it is easy. You can directly write the matrix. But if it is not standard basis, then you need to do a little work. For example, for the same problem, if the basis set is different, for example, let's say I'm taking the standard basis only on one side, but here I'd like to change the basis set. So here I'll change this basis set to 1, 1, and this one is 1.